So that's how sodium works. That's how it becomes an ion. It wants to lose an electron to look like, of appearance's sake, and we all know how that works, like a noble gas. Okay? The next one is sulfur. We're going to look at sulfur at this point. Sulfur electron configuration is 1s2, 2s2, 2p6, 3s2, 3p4. Now this is in column 6. All right? And that's why we end up with 6 valence electrons later. Just like sodium was in column 1a, that gave us a 1 valence electron. And shockingly enough, we have an extra electron dropped from it, so it didn't have that anymore. And so what they want in the valence shell, the valence level, the outermost level, to have 8 electrons. Well, the outermost level right here, or the outer electron configuration, is 3s2, 3p4. Well, that's 6 electrons. So, 2 options that sulfur has here: we can lose those 6 electrons, or we can gain 2 electrons to be full. And again, which sounds easier? Yeah. Gaining the 2. It's easier to deal with 2 than it is 6. So this is what's going to happen. It's going to gain 2 electrons. Now when it happens, that means you've got 16 protons here. You add all that together, including the 2 over here, and that gives you 18 electrons. In fact, let's take a look at the electron configuration here. 1s2, 2s2, 2p6, 3s2, and 3p4 plus 2 is 6. Looks like a noble gas, looks like argon. Its appearances are that way, and they are happy with that happening. But the deal is, we have 16 protons, 2, 4, 10, 12, 6, 18 rather, electrons. All right, and if you add those together, you have an overabundance of electrons by 2. So that is a -2 charge. So when you gain electrons, you become negative. When you lose electrons, you become positive. And we write that as S2 negative. Now you notice we didn't put -2. We put 2 negative because we're saying there are 2 extra negative charges. Okay? So if you make -2, I'm going to correct that on your homework. Make sure you understand that this designation has the term of quantity of excess charges. And because this has a 2 in there, we have to put 2 in there, but the 1 we have for sodium we don't put on because, like I said, about the whole algebra 1x. Okay? Now, the example that I give you in the script is finding the electron configuration. Oh, one more thing before I do that. These are negative ions, and they are called anions. And N is Greek for negative. Okay? All right. So aluminum, we're asked to find the electron configuration of the ion first. And we'll go and deal with the overall charge. We have to do that. So we go to this, 1s2, 2s2, 2p6, 3s2, 3p1. Okay? And this is in column 3, so it makes sense that the valence level is the 3rd level, 3s2, 3p1, 2 plus 1 adds up to 3. So that verifies what we suspect to be true. Okay? So 1s2, 2s2, 2p6, 3s2, 3p1. Now remember, it wants to look like a noble gas. So, one of 2 things is going to happen. It can gain 5 P's, or it can lose the 3s2, 3p1, because that'll leave this right here. And since you deal with 5 electrons here and 3 electrons here, it's going to be easy to deal with the 3 electrons. So aluminum, which by the way is a metal, and we'll make a point of that in just a little bit, is going to have 1s2, 2s2, 2p6 as its outermost level, because it's going to lose those right there. Now, aluminum has 13 protons, because it's element number 13. We add these up, 2 plus 2 plus 6 is 10, those 10 electrons. So we have 3 more protons, then we have electrons. So the charge for this is going to be positive. Now, let's take a look at something rather interesting here. Get back to the periodic table. We have sodium and we have aluminum. Sodium and aluminum are both metals and they turned out to be positive. Sulfur is a non-metal, because here's your staircase right here. This is on the right side of the staircase. That'll have be a non-metal, and non-metals are negative because they have lots of electrons in the outermost level. Metals, however, and even though aluminum's on the staircase, or aluminium as it's supposed to be called, it is instead of a metalloid, it's an exception to that rule. This is the only exception on the staircase. This is a metal, as you probably know, because you drink from aluminum cans when you drink cans of soda. The point being is this: because they have less or a very small number of electrons in the outermost level, they tend to lose them. It turns out it's like 4 is the threshold, although there's a couple of exceptions to that, which we're not going to get into just now. But this has 3 electrons here, this has 2 electrons here, there's 1 electron here, and these have 4 electrons here, they're metals. So these are all positive charges because they'll kick out 4 or fewer electrons. Over here, these are nonmetals. They lose 1 here, they lose 2 here, they lose 3 here, and they lose 4 here. Now for the nonmetals. So that carbon is the only non-metal out of it. This is a metalloid, these are metals, and then so on. So they'll have -1, -2, -3, -4. Well, how can you predict that? Very simple. If this is -1, this is in 7a, because you're gaining electrons, you're adding electrons, 7 plus 1 is 8. So this has to be a -1 for all these lines here. Because you have 6 in the outer level and you need 2 to be full, it's going to gain 2 electrons, that's -2, that's -3, and that's -4. Okay? +1, +2, metals, +3, +4, +5, it turns out, and floating is just weird. And I believe it is +6, it may have other charges as well, just like bismuth, tin, and lead all do. So, what you're going to do now is that you're going to be given some elements. And you're going to find the electron configuration of the atom and the ion both. Start with the atom and then work back to the ion. Give the number of electrons and protons of the ion, like I've been doing, and then give the charge of each problem. So, 5 answers for each problem. And you have 4 problems: magnesium, bromine, rubidium, and nitrogen. Have fun!